Next up is Bryan Fields W9CR. His talk is IPv6 in amateur radio.
I'm Bryan W9CR, and I'm local here in St. Petersburg, Florida. And I'm talking on probably not a very popular topic, I suppose. So this is IPv6, specifically what we're doing in amateur radio with it, which is unfortunately right now not too much. But I'm involved with a group here called HamWAN, and we have a deployment locally in Tampa Bay, and we're starting to do some stuff with it, and it's really going to be something we're going to see more and more about, and something we need to be aware of going forward. It's actually, believe it or not, been out for about 20 years now, so, 20 years. It's kind of an old, mature protocol at this point. So, anyways, my background is, it's up here, it's the same background I had last time. Not too much has changed. I'm just older. I've done a lot of stuff. I've run ISPs. I have a background in microwave network design, with emphasis on some low latency stuff. I do carrier IP engineering, so that's for service providers. Also do optical engineering, which is more like RF than really networking is. And we relocated here to St. Petersburg, Florida in 2005. So I really like Florida. I've been here. I have no intention to go back to Chicago where it's cold. Currently right now I work for, the current incantation of my company is called Nokia. And we do not make cell phones. Do not ask me anything about cell phones. I don't know about cell phones. If you want to talk everything about cell phones, packet core, I can talk about that. I'm on the AMPRNet Technical Advisory Committee, which is a position of basically no real power to do anything. I got my name on the website, and we kind of help out people from time to time. If you need something related to that, you can always email me, and hopefully I can see if I can contact the right people and do that sort of expediting, really. So, well, let me ask this. Who here actually read my my paper in the book? Oh, wow. I figured it'd be like 2 people. Thank you. What I said I wanted to do was do a talk on IPv6. I think around Dayton, I think I said, hey, this would be something that I'd like to do for DCC. It's something I haven't really seen anybody do. And so I said, I'm not really one for writing. I detest writing. I hate documentation. I'm just one of those people, typical engineer. So they came to me and said, hey, we've had one person submit something for the proceedings. Could you write a paper? I said, sure, okay, I'll put together 5 pages. And somehow it ballooned into, I think, one of the largest things in there. I apologize for that, but there's just so much on this topic. I think, one of my first presentations I went to on IPv6 at what's called NANOG, the North American Network Operators Group. So all these people that get together that are ISPs and have their convention. It was about 2 hours, and it still didn't cover everything. There's a lot of stuff here, and this is going to be very abbreviated. So we have a demo set up in the other room, and I'm happy to talk, about that and take some questions here and there on it. So I'm going to go through a little bit of history of what we call IPv4, which is our legacy internet protocol. It's 128.0.01, all that stuff that we know, and how this reflects itself in amateur radio today. Do a slight overview on IPv6. This is going to be very high level. If you've never seen IPv6, you're probably not going to get too much of it out of this. It's to get your appetite wet to maybe do a little bit more reading on the topic. And at least the thing I want you to take away from this is start asking vendors, hey, do you support IPv6? And right now, in amateur radio, pretty much nobody does. With the exception, I think, maybe Northwest Digital Radio and a few people like that that are using Linux as their platform. And then I'm going to talk a little bit about HamWAN Tampa Bay, where we're at with our IPv4 or IPv6 deployment. And, I think when I gave this talk, I gave a talk on HamWAN at Dayton, we had just gotten it after many years of struggle here in Tampa. We got it online and had finally some users using it, and now we actually have some really interested people making use of what we have out there. It's great. So, little IPv4 history here. You originally had the internet, and it was, well, I won't say it was void and without form, but it looked like this. So this was 1977, the AMPRNet logical map, or ARPANET logical map. AMPRNet didn't exist at this point. And this ran something called Network Control Protocol. And surprise, surprise, NCP was the first iteration of a internet protocol. And it had serious limitations. It just didn't scale. It worked fine for, this small network, but they were starting to run into scale issues even on something that small. So a new protocol was born. It was IP. It wasn't called IPv4. It was just Internet Protocol. TCP IP is common, or UDP IP. So they started deploying this, and on January 1, 1983, about a year and 6 months before I even existed, they shut off NCP. It was called Flag Day. This is on Wikipedia, which is, of course, a very accurate reference for this stuff. It was shut off. IP was turned on. And at this time, addressing for IPv4 was classful. So you got a, 1/8, 2/8, 3/8 sort of IP address. You couldn't get anything smaller if you were a network. And HAM's got 44/8, thanks to HAM KA6M, Hank Magnuski. And we have that recorded about 1981. That's an amazing resource that amateur radio has right now for IPv4. Unfortunately, we have nothing allocated specifically to ham radio for IPv6. We kind of missed the boat there back when planning was taking place in about 1995 or so. So moving forward here, this is the internet, and you can see here, I don't know if it shows up very well. It looks like there's probably a crack in the screen, I think. But this behind here is actually what the internet looked like around 1997. It was one of the internet maps in 1997. So we have this, exploding growth happening in the internet in the mid-90s. And we're facing limits of our protocol again. We can see, hey, wait, we're allocating stuff. We're going to, in 5 years, run through all the IP space that we have. This is a problem. It's going to keep us from being able to grow. And very importantly, talk end-to-end. It's one of the key goals of the internet is end-to-end communication. Any station can talk to any other station. And unfortunately, in today's modern internet, we've done a lot to break that. But IPv4, we're allocated on what's called a classful basis, which is your class, I think we've all heard of Class A, Class B, Class C networks. And around 1994, there was some work done saying, well, do we need those fixed subnet sizes? Does everything always need to be that size in allocations? And the answer was no. So something called CIDR, or classless interdomain routing, was born. Our routing protocol on the internet changed at the time. A new protocol was developed called BGP. It's still in use to this day. It's still used for IPv6. It's actually used for about 50 other things as well. It's a very extendable protocol. And what you're going to notice here is the stuff that's been coming out in terms of new protocols now, basically from the mid-90s, is very extendable. You don't have to reinvent the wheel. You can just add another, TLV or another data point to it, and if the router doesn't understand it, it just ignores it. But if the router does understand it, it can process it. So there's no reason to have to come up with something brand new. We can just extend it very easily. So even with this, what's called CIDR, classless interdomain routing, the allocations are still growing. We're still burning through IPv4 space at an alarming rate. And this is around the same time that we set up what's called IANA, the Internet Assigned Names and Numbers Authority. This went from being, unfortunately, pretty much with one person's death, it went from being one person doing it for all the educational networks and everything that was on the internet at the time to being transferred to a actual authority that went through it. Under-chartered by the U.S. government, there's some stuff going on where the U.S. is going to be getting out of that and actually handing it over to, I think, a worldwide, government's committee. De facto, it works like that now. So we had some work being done here too to say, well, maybe we can do something. Maybe you don't need a real IP address. Maybe we can do something to translate a group of hosts behind a router to an IP address. Now, you're not going to be able to talk to those hosts directly, but they can talk to other hosts on the internet directly. And this is what I call the first major breaking of the internet. And it's many-to-one network address translation, also known as port network address translation or port address translation. This is NAT. This is a hack. This fundamentally changed and broke the internet. And we all deal with it to this day. If you've ever tried to, get your all-star box working between your firewall or your router at home and had to do port forwarding, it's because of this dirty, dirty hack. So the other thing the internet's struggling with is something called routing table bloat. So what we have is, because of the way that we're allocating IPv4 addresses, rather than just giving them a huge amount of address space to a service provider and saying, go ahead and use it, or to an end user, go ahead and use it, and we're never going to have to reallocate it, they give small blocks out. And as you need more space, you go and request more blocks. Well, each one of those blocks takes up space in the routing table on the routers that make up the internet. And I won't say it's 640K, but we cross a boundary of 64K. I mean, there's 64,000 individual routes that make up the internet. And that was pretty significant because there were a lot of routers, a lot of big, expensive routers of the day, made by companies such as Cisco, that could not handle greater than 64,000 routes. Needed significant upgrades, millions of dollars of upgrades across the internet to make that happen. So let's do a new protocol, something that will prevent us from having to go down this path again. And unfortunately, IPv4 is not very extendable. It is what it is. It was pretty much put together by about 2 people. And our 32-bit address space, the 4 billion addresses that we have, was chosen and said, well, yeah, that's probably enough for what we're doing under the guise of ARPANET. For a global network, it doesn't work out at all. So this started some work happening, and there was a ton of different protocols. There was one called Tuba that was proposed. There was some other funny names that came out, all out of what's called the IETF, the Internet Engineering Task Force, just a group of neckbeards that get together and argue incessantly. It's actually kind of fun to go to one. If you don't get yelled at, you're probably not doing something right. So there's been a few fist fights over stuff, which is interesting. Generally, that doesn't happen anymore, though. People are a little more restrained. But IPNG, and keep in mind, this is the mid-'90s, so what's the big thing on TV for all the nerds? The next generation. So IP, the next generation, begins in 1993. IPv6 comes out of that. There was an IP version 5 in there, but anyways, it's IPv6. Version 6 comes out of it in 1995, is actually standardized. Now, if you remember what I said about protocols that are coming out now, they're extendable. So there's always stuff being added onto IPv6, and it's kind of interesting. Everybody got a little something they wanted out of it, and everybody didn't really like it because they didn't get exactly what they wanted. But we see the dot-com crash kind of seeing IPv4 allocations level off around 2000. It was going up at an exponential rate like this. Now we're kind of still going up, but we're not going up anywhere near as fast because all that venture capital money dried up, and people don't want to have their groceries delivered by sock puppets and things like that. So the other thing is we have NAT, which really reduces the pressure on IPv4. Most people now, you're not getting a subnet routed to your house from your ISP. You're getting one IP address, and it's up to you to make use of that for all your routers, which is really interesting because the cable companies at this time had the idea, you know what, if we're selling you cable service, you get to use it with one computer. If you want to use additional computers at your house, you have to pay more money. And NAT they actually had stuff to see if people were using NAT, and it was kind of an arms race between the consumer router vendors and the major cable companies going around and harassing their users. it's not an issue anymore. People could care less. I mean, the cable companies are even providing Wi-Fi and doing all this yourself, so they have a better view inside your house now. But at a time, it wasn't just the cable companies, the other ISPs saying, well, you buy one service, you get one computer, if anybody remembers that. So because of this, IPv6 doesn't take off as expected. This is kind of mostly due to confusion and something we know all too well in ham radio, apathy. The idea for deployment of IPv6 was actually supposed to be pretty simple, something called dual stack. And what that means is you run IPv4 on your computer and you run IPv6. IPv6 and IPv4 can't talk directly to each other. So you get an IPv6 address and an IPv4 address. And sometime in the future, maybe around 2005, we'll shut off v4 for good and you'll just use IPv6 for everything. Yeah, that didn't happen. So come around 2008, most larger ISPs, these are what are called your tier 1 providers, your tier 2 providers, your big ISPs, your carriers, that, IPv4 exhaustion, we can't really do any more hacks. This is, we can do the math and we can see where that becomes 0 and where it crosses that x-axis there, or y-axis. But a lot of the small people are saying, well, I'm going to be dead by the time I need IPv6. And nobody's deploying it. From enterprises, things don't support it. I think Windows XP finally supported IPv6 kind of, but it didn't exactly work. There's a lot of experimentation going on, but nobody had really been able to deploy it. At least anyone that wasn't an ISP, and still, at the time, if you looked at the IPv6 internet, the largest and most used protocol on the IPv6 internet of 2008 was ping and traceroute. And the other real problem that we faced of IPv6 is that the internet of the day in 2008, even in some cases now, IPv6 just didn't have the performance of IPv4. This, multiple things affected this. Routers couldn't route it as fast, couldn't do it in line speed. Some of the older Cisco routers, for example, they would be able to route IPv4 as fast as it came in. But IPv6, it would just hit the CPU and you'd get about 10 meg out of it and the router would fall over on itself, even for your expensive routers. So that, overlay networks of IPv6 over IPv4 would make suboptimal routing. That breaks the internet. Please, it does. Understand this. It's not a solution. It's not security. And I can't say who, but I'll just say I do work in the MSO industry, which is the cable industry. Large eyeball ISPs, these are your huge ISPs, are using the 10/8 private IP space. They have it federated in 8 to 9 different pieces used 100% internally. They need IPv6 just for management. They can't address all the devices on their network with private IP space. It just simply doesn't scale. That's 16 million devices. Well, when you have 50 million subscribers and 2 devices per subscriber, you can't manage the stuff in your network management system if you can't address it. So we have IANA, the Internet Assigned Numbers Authority, and what are called RIRs, Regional Internet Registries. Has anybody heard of ARIN? American, okay. So American is one of the 5, ARIN is one of the 5 regional internet registries. The other ones in Europe is called RIPE, which I believe is a French acronym. There's APNIC for Asia, and then we have LACNIC for Latin America and the Caribbean, which is really weird because if you're in Puerto Rico, you can get space from either one, either from ARIN or LACNIC, depending on your business. And there's one other one, AFRINIC for Africa. So we have the IPv4 runout timeline now from these regional internet registries. And 31st of January, 2011, IANA allocates out of the last 7 blocks, they had /8. So what happens is IANA, I should backtrack here, IANA gives blocks to the regional internet registries for them to divvy up in their region. And they allocate 2/8 blocks to APNIC out of the last 7 blocks they have available. So this triggers what's called the run-out policy, meaning when we're down to 5 available /8 blocks, the 5 regional internet registries, they get 1 each. And that's it. Game over. IANA has no more space available to give to the registries. Now the registries give it on to their users in their local regions. They're good for another few years. On the 3rd of February 2011, IANA makes a press release. The IANA IPv4 free pool is now depleted. Go home. ARIN enacts a policy once this happens to further restrict IP requests from its members, people in the US here. So legacy allocated IP space now commands a premium. There begins a market for IPv4 space. You can go buy it. And this is special because the 44/8 block that ham radio has, being it was allocated before ARIN was out there, is owned by ARDC. It's a nonprofit corporation in California. Whereas if you get space from ARIN or any of the regional internet registries, you don't really own it. You can't sell it. You have it under license. We own it as ham radio. That's very important. IPv4 becomes a commodity, and this is a real cost. You can go and buy it. ARIN is still allocating space, but by April 2014, they reached their last /8 available, triggering more policies. So a /24 is now the largest initial request you can get. That's also the smallest subnet you can route globally. Before, you couldn't go to ARIN and say, hey, I need such a small amount. They said, we'll get it from your ISP. We give out bigger swaths of space to people that are interconnected with multiple carriers. So June 2015 rolls around, and ARIN has its first unable to allocate. And this means somebody requested, I believe it was a /17 request, and ARIN could not allocate this. They said, we just don't have that to give to you. Now, we're still getting /24s and smaller subnet blocks, but they didn't have a large amount to give to somebody. So they said, we're going to waitlist you, which you're not going to get it, kind of. So 24 September 2015, this is a major day. The ARIN address pool reaches 0. This is the end of the IPv4 internet. Some of the other regional internet registries have run out beforehand, but as America goes, most of the world goes as well. 44/8 now is worth probably about $100 million to $200 million. That's a huge endowment to amateur radio. This is scary because I am listed on the Technical Advisory Committee. Like I said, position of no real power on their website. I'm at NANOG in was it Seattle, Bellevue, Washington, a couple of years ago, right around the time this happened. I'm walking down, just walking outside. They have like a coffee bar there, and somebody from a company called Hilco Streambag comes up to me, says, Mr. Fields, Mr. Fields, Mr. Fields. Yeah, who are you? Do I know you? Oh, no, but we know you. I'm with Hilco Streambag. I'd like to talk to you about the 44/8 block that, you're on the committee for. I said, I've never met you in my life. How do you even know what I look like? Oh, well, we did some research. I said, wow, okay. These guys are a brokerage for IPv4 space. So the solution here is IPv6. And so, look, it's the de facto path forward. We had time to debate this. That time was 1995. Unfortunately, I was just getting licensed, and I was 9 at the time, so kind of wasn't able to do that, which is really scary when I consider I've been licensed for more than 20 years. This is not open to debate. It is what it is. This is going to be what we have to do going forward. Major carriers are deploying it. So why is it different? What do we gain here? And you can see what we gain is we go from 32 bits of IP space to 128 bits. Now, that's a little misleading, and I'll get into that in a minute. Because the smallest subnet is a /64, even though we have 128 bits available. So that means we're going to have something like a /64. We're going to have 2 to the 64 hosts on a subnet. We can always go smaller than that if we want to, but we break a lot of things. So in general, take away from this, the smallest IPv6 subnet is a /64, meaning we really have 2 to the 64 address spaces available for allocation. But even doing this, each human on Earth right now, and I think there's about, what, 7 billion of us, when I did the math on this a couple days ago, we have 100 million subnets of /64 available for everybody. This is a huge, huge, huge number. I mean, I can't fathom it. Most other people can. I can't even fathom 100 million subnets, let alone the true size of this. Now, the nice thing here is ISPs, you go as an ISP and say, hey, I'm an ISP. Okay, the Regional Internet Registry gives you a minimum of /32. Most of the time, the larger ISPs are getting /19s, which of IPv4 would not be that much. It's good size. Of IPv6, it's huge. That means an ISP has to announce to the internet, here's one route and all of our customers are behind it, rather than here is, 1,000 or 3,000 routes that are carved up of IPv4 and our customers are behind that. This makes the routing table go down. Actually, I pulled this the other night. We're under 32,000 routes for the global IPv6 internet. Right now, we're at 625,000 routes for IPv4. And this is significant because a router has to do a lookup every time a packet gets forwarded. So we have auto configuration without DHCP or with DHCP, either or. This is a nice thing. We have some new types of IPv6 space. We have what are called link local addresses. They're only valid on an Ethernet segment. So between two computers connected together, it has its own address that's only valid on that segment. And because of automatic configuration, this means they can talk to each other without, you just plug it in and they can form an adjacency. They can see there's another host there. You can't do that with IPv4. Global unicast routes are what you're going to get, and we have multicast improvements. It's possible to make use of it without much configuration. IPsec, the security protocol, is mandated as part of IPv6. You can't have a valid IPv6 stack on your software without IPsec support. Hams use AH mode only, and I actually did some stuff with the P25NX guys to get it legal over amateur radio frequencies so that we're only authenticating the packets, we're not encrypting them. So the other cool thing we've done, you can see here, the IPv6 header is a little bit larger just because our source addresses are larger. But it's a cleaner layout. We've eliminated a number of things here. The checksum, identification flags. And if you notice the way that it's laid out, this makes it a lot easier to make a custom ASIC that is able to do processing in real time. This is important. So this is what an address actually looks like. It's written as 8 blocks of 4 hex characters. And what you're able to do is simplify when you have all zeros in there. You can do this once in the address and put a double colon in there, and it'll pad it out when you type it. This is what it actually maps out to. So, subnetting in IPv6. This, as I said, a little bit different. You can go all the way down to a /127, to have 2 hosts talk to each other. However, you should really only go to a /64. Many routers and chipsets that are out there, even software stuff for Linux, can't handle a large number of routes if they're greater than a /64. Probably one of the most popular chipsets out there today is Broadcom. It has issues when you get above a /64 for IPv6 routes. So this is very basic switches and things like that that everybody uses. And this might be a little confusing. The smallest maximum transmission unit you have to be able to support over a link is now 1280 bytes. Used to be 64 bytes was the smallest you could support in IPv4. This is nice for people doing embedded development. You can emit, if you keep your packets under 1280 bytes, you don't have to have what's called path MTU discovery to figure out the maximum transmission unit over a given path. We can support packets up to 4 gigabytes, which doesn't make any sense, but maybe in the future we'll need it, so that's what we can do. This is nice. There's no more broadcast traffic. It's dead. This means no more broadcast storms. That's a thing of the past. We have, instead of ARP, we have Neighbor Discovery Protocol. That doesn't use broadcast, it uses multicast. So The awesome thing we have is auto configuration. And that is, IPv6 enabled hosts can talk without a router. You can just plug two Raspberry Pis in together and they'll form an adjacency. You can SSH from one to the other if you know its IP, figure out its IP address in the neighbor table. So the MAC address is used to create what's called an EUI64 address. And you can see where it takes the MAC address, breaks it up, and then puts this at the host address. Won't go into this, but you can read up on this on the internet if you're curious. But what's important here, this only works on /64 subnets. This is why you use a /64 for your smallest subnet, because you want to take advantage of this. It's ideal for ham networks. You don't have to do funky things, breaking up 10/8 of IPv4 space. You can just use this, and it's guaranteed to be globally unique if you do that. And you can also assign stuff with the HCPv6 if you want to. That's what we're doing at HamLAN. So you got to have DNS, which is domain name system. It does your IP address lookup, because this is your typical IPv6 address. I can't remember that. Can you? About the only one I can really remember is Facebook, because it ends in Facebook. So we're seeing a new record added to DNS called a quad A record. I don't know how to write it. It's pronounced a quad A, but it's written an A record, or A. I might have accidentally an A there. So if a resolver finds, your computer finds a quad A record, it'll prefer IPv6 in most cases now. So reverse DNS is still what's called a point to resource record, a PTR record, but each digit is its own field. And you can see here, this is an IPv6 address. This is what it expands to in the zone file. People are doing a database lookup for this. But unlike IPv4, you don't set it up for all IPs in the subnet because it's a /64 subnet. Even using a couple bytes for DNS, you're going to be over 400 exabytes in size. And I believe that's gigabyte, petabyte, exabyte. So really, unless you're Google, you probably can't do that. And that's only one subnet. The other real issue here is you can do on-the-fly creation in some stuff, but this shows that there's some security issues there for doing that, because you can exhaust your resources by doing repeated lookups for different addresses. So, oh, sorry, NAT works and I don't care. Seriously, why can't we just do NAT? Simple, NAT is evil. Here's all the reasons NAT is evil. If you take one thing from this talk, go home and when somebody suggests NAT, tell them NAT is evil. Bryan Fields told me NAT is evil and here's the reasons. So this fundamentally changed the internet. It broke end-to-end connectivity. This is not what the internet's about. NAT is not a firewall. If you want a firewall, get a firewall. NAT is not a firewall. NAT must maintain state. It doesn't scale well. Carrier-grade NAT breaks inbound connections with no control over port forwarding for most people. This is the average user in Europe right now. Scaling of NAT is hard to do. I work for a company that makes routers. Large-scale NAT requires really expensive equipment. So ignoring me doesn't make the words I'm saying less true. So IPv6 and ham radio. 44/8, well, we probably don't need v6, right? Wrong. You need it to talk to the internet, and you're going to need it to talk to the internet more and more. Not so much in the US. Well, even so much in the US. Your cell phone all has IPv6 enabled. You're going to need it very, very shortly. NAT's making it hard. As I said, it's evil. In many cases, the applications we have as hams, the embedded devices, all this stuff that hams have, might support IPv4, but it certainly doesn't support IPv6. And the stuff that does is few and far between. So you need to ask people, hey, do you support IPv6? Ask our vendors, when you're at Dayton, do you support IPv6 on this wonderful newfangled internet-enabled thing? Well, we need it to be able to use it over the internet. A VPN overlay is not a valid solution for most of this. And mobile apps need it right now. So you're going to need to learn, if you're programming, how to support IPv6 in that. And the Raspberry Pi makes it easy because it's Linux. Anything that's Linux makes it easy. But your embedded little PIC devices and things like that, you're going to need different libraries. You might even need a slightly more powerful device. But web pages need to support it. FCC.gov actually supports IPv6. Every time I do a call sign lookup, I use IPv6. Pretty cool. Probably the problem is ARRL and Tapper don't even have it enabled. Maybe we could look into that. So networking standards for ham radio variant support. I'm not going to go through each one here, but I'm just going to say, come on, AX25. I didn't even investigate it. It's too slow to do anything with. I think Arden would benefit from IPv6. I haven't seen them doing anything with it though. I'm a bit critical of mesh networking anyways. Ham WAN, we can do dual stack today. All of our routers support it. So World IPv6 Day was kind of the IPv6 coming out party, if you will. Cool thing right now, mobile networks are 90% enabled. All stuff on mobile networks is v6. 50% of all traffic on mobile networks right now to the content delivery, the big content networks, your CNN, your Netflix, your game providers is all on IPv6. Over 30% of all end users on the internet now in the US have IPv6. Doesn't necessarily mean they're making use of it, but they have it available. Most of Europe right now doesn't get an IPv4 connection when you get internet service. You get IPv6 and they use technologies such as MAP-T, DS Lite, and carrier grade net to kind of make all this stuff work. It doesn't work very well. For anybody that's done 2 or 3 levels of NAT deep, we have it working kind of in there right now for the P25NX stuff. It doesn't work that well. It's fun to troubleshoot. The cool thing is most of the cable companies right now are leading in the US with this. Some of them aren't, but most of them are. If you're getting new service, even though you're not making use of it, it does support IPv6. Your commercial colo and your hosting places, they do v4 and v6 now, dual stack. And if they don't do v6, find a better colo. That's unacceptable. Here's our current usage. And you can see it kind of went, ping, trace route, and then it's going up, like the internet use used to go up. And we're going to see IPv4 at some point start doing this. And that's going to be kind of cool to see. So the other thing I want to talk about, and I think I have about 10 minutes, right? Thank you. So give a little update on ham WAN, which is a multi-megabit network standard for amateur radio. It's a very loose standard. It was started by a brilliant group of guys out of Seattle, basically saying, let's make a system so that we can get internet access over amateur radio frequencies for hams, or network access for hams, whether it connects, it's connected to the internet. So you can get on the internet or you can stay on their network, whatever you want to do. Ham WAN doesn't care. We just route the packets. If you build it, people will figure out what to do with it. I like building networks. I don't necessarily like getting on the repeater and talking. I'm one of those people. So where we're at right now, this is our coverage area. And we're on a building right here in downtown Tampa. And FYI, we're right here right now, if you can see that. So just right there. So we're in the coverage area, and this is assuming you're 30 feet up and have one of our typical dish setups, about a $200 setup. We figure most hams can get up about 30 feet pretty easily, and so long as you're not in a tree, you're okay. We've been online since May 2016. We now have, I think, Ryan, you have 2 sites online, right? 4. Wow, okay. We just had 100% growth. It's amazing. So, we have some very cool things being done with this. I like building it, and other people are going to like using it. We're using it to link DMR. We're using it to link All-Star. We have the P25NX guys using it. So it's very cool. But we have a /20 from ARDC, the AMPERNET IP space of IPv4. And we have IPv6 from our upstream. They gave us a /48, which is kind of standard. They said, well, if you need more, we have, I think they said they have a /24, so come and ask them. They're very easy giving us that space. And we're planning to expand to St. Petersburg and Sarasota in the next year. We have a site in St. Pete here that's very close to the hotel. We just have to get that online, and we kind of sat down and said, hey, it'd be really cool if we could do this before DCC came, and then life came to pretty much everybody involved and said, no, that's not going to happen. DCC got booked the same time that I had my conference in Las Vegas. So Thursday I'm flying, 7 a.m. out of Vegas to St. Pete and having a 2-hour delay for a burnt-out light bulb on an MD-80 in Dallas. So we're all under the umbrella of a group called Florida Simulcast Group. It's a 501c3. HamWAN has its own group that it works with and does standards. We use the HamWAN standards, and we operate under this group. At some point, maybe we grow, we decide we need to spin it off. But right now, all the people that are involved in it say, hey, this is good. So what I did for this, and we don't have IPv6 enabled everywhere just yet, and I actually have to stand up the DHCP server. But we do have stateless auto configuration working on HamWAN right now. We get a /48 from our provider, and the idea here is, this is maybe an idea how you would deploy it. I'm not saying that you have to do it exactly like this. We got a /48, and I'm actually using, I'm going to show some example IP addresses in here. It occurred to me those are actually our IP addresses we're using for IPv6, so please don't use those somewhere else. If you do, it'll cause, well, probably won't cause any problems for me, it'll cause problems for you. And what we decided to do is, because the /64 is the smallest subnet that you can use, we want to give out a group of subnets. So if you put a client on, you know what, maybe we should give you a number of /64s. Well, you can do something called prefix delegation, meaning I'm going to use DHCP version 6, give you not only a IPv6 address for your interface, but give you a group of subnets you can use behind your router for your internal networking if you want. And we just use DHCP. Even if we assign it statically, we still use DHCP to push it down. We'll do a static DHCP assignment. It makes managing the network a lot easier. So that means let's do a /60. And this gives 16 /64 subnets for a client. And we're going to divide up our /48 in a logical manner. Very importantly, we're dividing it on what's called nibble boundaries. A nibble boundary is 4 bits. 4 bits corresponds to 1 digit of hex in the address. So it makes it very easy to read. You don't have to do all kinds of math in your head to figure it out. How many future sites are we really going to have? And we sat down and said, if we got 16 sites, we'll go back and get some more address space. I think that's an acceptable number to use. So we decided on a /52, which is the next nibble from a /48, 4 bits more, 16. And then per site, per 52, we divide it into /60s, which give 256 possible subscribers hanging off one of the HamWAN sites. And, if we exceed any of this, we'll just go back and say we need another /48. It's, IPv6 is like a Pez dispenser. You hit it, you get one, you move on. So our strategy, we said, okay, 52 for a site, what's that look like? And you can see, because we're doing this based on the nibble boundary, here is our delegation from our provider. Here's the first subnet. There's site 1, and here's site 2. You see how it goes 2, 3, 4, and then over here it does that. So it makes it very easy to see what site something is on looking at the address. So we need to instantiate a central DHCP version 6 server to assign the /60s for delegation. And basically what happens is your client comes up, gets an IPv6 address for the local subnet, and then routes IPv6 to it. The router will automatically do that. So typically out of this per site, rather than 256 individual subscribers on a site, clients, we use one for loopbacks and management and whatnot, meaning we can have up to 255. If we have 255 people on a site, man, that'd be amazing. We probably wouldn't be able to scale to that. So this is what somebody would look like for a site. Pointer died here, but you can see what you're doing here is if you look at this nibble here, 0, 1, 2, 3, all the way to, because it's hex, FC, FD, FE, FF. If you see right here where these are, only those digits change. This makes it easy to read for human eyes. So that's our deployment strategy for HamWAN Tampa, where we're at, where we've come. Please ask your vendors about it. And I finished on time. So question, I got time for questions, right?
Just one is an observation, and the second is, I suppose, actually both observations. One is it takes about 3 seconds to do a ping over 9K6AX25 packet. It's pretty slow, as you thought.
Over AX25?
Packet. Yeah.
Wow. Okay.
About 3 seconds to get a ping. That was came with TMD 710. The other thing is, you didn't mention it. It's possible to get if someone wanted to experiment with IPv6 at home, you could access a tunnel broker. And there are those services out there. I just wanted to make that point.
Yeah. Unfortunately, I use the tunnel at home. That's a good point. Over there.
Do you have a good reference for a home network? I'm running behind a pfSense firewall. A good reference to work on getting my home network switched over to IPv6?
You know what? I can find something. I'm in the demo room. Can you come by and we'll talk? Awesome. And
yeah, I'm not quite sure I heard one thing right there. I didn't understand it right.
Sure.
Did you say you were aligning the bytes on a nipple boundary?
yeah,
Nipple?
nibble.
Oh, nibble, not nipple.